So let's remind ourselves of a few things about the gradient and directional derivatives in general. So let's say it's not the part I want. Some properties of the gradient. And first, a couple reminders. So just a reminder, the directional derivative of the function f in the direction of the vector u is equal to the gradient of f. Now, I should point out, this gradient of f is the gradient, then you plug in the point you're finding the derivative at. So sometimes people write it as like the gradient, the directional derivative in the direction of u of f at the point P. So you got your gradient evaluated at P, and then we're dotting that with the unit vector u. And then sometimes we like to write that the directional derivative, the other way we calculate this is the magnitude of the gradient of f times the magnitude of the unit vector u, which should always be 1 times cosine of the angle between them. Good to keep both of these definitions in mind. Where this one's the one we're always typically going to use to actually calculate the directional derivative. This one's idea becomes important sometimes when we're trying to like say something is true about something. So definitely keep this idea in the back of your mind. So this tells us a couple things. First of all, thing one, the maximum direction. I know we said this at the end of last class. I'm repeating myself because I think it's important to say this again. So in case you're like, why is he saying this again? That's why I'm saying it. So the maximum directional derivative, again, when you think of the maximum of this derivative, you should imagine that you're on some hiking hill out somewhere and you're trying to look in the direction that's going to be the steepest way up the hill. That's what your maximum directional derivative is. It's the direction you can go. So, well, I should say, I should pause there. It's how steep the slope is in the direction that's the steepest, right? The directional derivative isn't the direction, it's the slope, right? Your derivative is your slope, your rate of change. So the maximum directional derivative is the slope of your function f in the direction that is steepest. And importantly, will occur when, well, if we're trying to maximize this directional derivative, the only thing we really have a choice about is the angle between the gradient and the vector that we're the angle between the gradient and the direction we're taking the derivative in. And to make that as big as possible, we want this cosine of theta to equal 1. So it's going to occur when cosine theta is equal to 1. In other words, the angle is equal to 0 radians or 0 degrees. In other words, the gradient and the direction point in the same direction. Another way to say this, kind of the usual way of saying this, is the direction of, I'm trying to write the right words here. Yeah. The direction of maximum directional derivative value is just the direction of the gradient. Whichever direction the gradient points in, that's the direction that is the steepest way up the hill. It's going to maximize the derivative or the slope. So the usual way of writing this is the gradient vector divided by its own magnitude. Because as usual, typically when we're asked to give a direction vector, we want to give it as a unit vector. Question or comment? Correct. So the thing is, we're saying what u is. So if I said, like, if I gave you a function and said, tell me what u is that's going to point in the direction of maximal increase, you would say, oh, u is equal to the gradient of f divided by its own magnitude. We'll do an example in a minute, I promise. And then the other thing we want to say is, sorry, I put a 1 here. I feel like that one was kind of necessary. The maximum value of this directional derivative. So the maximum value or slope of the directional derivative. Well, again, if we take a look at this here, if we're trying to maximize this directional derivative up here, we've got the magnitude of the gradient times 1 times something that's going to be as big as 1 at the most. So the maximum value this can have is just the magnitude of the gradient vector. So it's the magnitude of the gradient of your function. So what's kind of nice about this is that if you've done the first part, like if you found the direction of the maximum increase, you've also already found the answer to the second part of the question, which is what is that value? It's just whatever thing you're dividing by typically. Let's do an example to kind of make this make a little bit more sense. So let's say that we've got the following situation here. We've got a function f of xy equal to 3xy minus x squared. And we're going to ask the following. What is the direction from the point -1, 1 that this function increases most rapidly? Or in what direction is the maximum rate of change? Or in what direction is the slope the steepest? All those questions are the same question. There's lots of different ways of phrasing it. Okay, so all we're going to do is we're just going to find the gradient. So step 1 or part 1, find the gradient of f. Well, that's going to be, let's see, it's going to be the partial of f with respect to x and the partial of f with respect to y as a vector. So it's going to be, let's see, the derivative of this with respect to x is going to be 3y minus 2x. The derivative of this with respect to y is going to be 3x. So there's my gradient in general, but we're specifically asking at this particular point. So we're standing at the point 1, -1, or -1, 1, sorry. And we're asking, okay, if we're standing at that point on the surface, which way do we face so that it's the steepest incline? Well, that's going to be the gradient with that point plugged in. So our gradient of f evaluated at the point -1, 1 is going to end up being 3 times 1 minus 2 times -1, and then 3 times -1, which is going to equal, let's see, that's 3 plus 2, so that's going to be 5, 3. It's a -3, sorry. Now we're not quite done. Although I will tell you, some people are totally fine with accepting this answer, right? You're giving them the direction. You're saying point this way, from where you're standing, you're going to be going 5 in the x direction and -3 in the y direction. So you're kind of going to be going, if we're thinking about standing on x, if we're thinking x is that way and y is that way, I'm going to be going 5 that way and 3 that way. So I'm kind of going like in that direction, right? 5 in the x direction, -3 in the y direction. I could just leave it like that. But most of the time, people want you to normalize your vector or unitize your vector, make it a unit vector, because then all the answers are going to be standard. Really, that's kind of the reason why, actually, is so that I don't have to look at 10 different answers and be like, yeah, that vector is true. Yes, that's a multiple of it. Yes, also is that. I want all the answers to just be one. It's also easier to program. So instead, we're just going to say our direction vector, which you could call u if you wanted to. U is going to equal the gradient of f divided by its own magnitude, which in this case is going to be the vector 5, -3 divided by its magnitude, which is the square root of 5 squared plus -3 squared, which ends up being, I'm going to write this as 1 over the square root of 25 plus 9 is 34 times the vector 5 comma negative 3. So there's the unit vector that points in the direction of maximal increase or most rapid increase. And now this next question I'm about to ask, we've already written down the answer, but I'm still gonna ask it. So the other question is, what is the maximum rate of change of this function f of x comma y at the point negative 1, 1? And we've already written the answer on the paper, just not by itself. The maximum rate of change is always going to be the magnitude of the original gradient vector that we found. So in this case, it's going to be the max rate of change is going to be the magnitude of our gradient, which is just going to be the square root of 34. The gradient magnitude we already found. That's kind of most of the whole picture with the gradient, right? The gradient is the vector that points in the direction of max. Oh, there's one other thing to say here for sure. The gradient points in the direction of maximal increase, and the magnitude of the gradient is the steepness of that slope at that point in that direction. So if you were actually standing on this made up surface at the point negative 1, 1, and you looked in the direction of 5, negative 3, so kind of that way, the steepness of the slope would be the square root of 34, meaning if I move 1 in that direction, I'm going to be going up almost 6. It's a pretty steep slope, right? Not something I want to hike. The other thing we should know about is the following. So I'll show you this one and then I'll kind of do one too. So there is a third important property of the gradient. It involves level curves. So let's go back to one of my favorite examples, this f of x comma y equal to 9 minus x squared minus y squared. You don't have to draw it again, but I'm going to draw it again to help remind you what it looks like. So here it is. It's this, downward opening paraboloid. It's like that, kind of like that, like that. It's got this circle at the bottom. And it's got some level curves, right? And the level curves are circles. So down here at the bottom, where like say z equals 0, my level curve is the circle of radius 3. It's x squared plus y squared equals 9. And then up a little higher, say like it's z equal to 4. Sure. So I can do this well. So here's the level curve at z equal to 4. And that's a circle of some smaller radius. If we can go higher, we can go to 6. And say, yep, there's level curve at z equal to 6. We can even go up to 8. You can even go up to 9, but at 9, you'd have a circle of radius 0, which is not very exciting to draw. Okay, let's see if I can do the hard part. Let's see if I can actually draw these on a two-dimensional XY plane as just circles. So same deal. So we know that when z equals 0, we get so I'm going to be smart about this and not try to make it look too perfect. It doesn't really need to be that perfect. So here's my, geez. There's my z equals 0 level curve. And then here's my z equal to 4. Yeesh. And then z equal to 6. They should be very nicely concentric circles. And then finally, z equal to 8. Okay, that's it could be better, but it's It's all right. Those look like circles. If someone asked you what those were, you would say circles probably, or an attempt circle. So if we're at the point, say x is 1 and y is 2, and z is 4, so at the point 1, 2, 4, kind of like right there. So I'll point out here that the gradient is going to point exactly that way, right towards the peak, because that's going to be the direction of steepest increase. So right here, we've got the point 1, comma 2. So the point here is that at the point 1, comma 2, or 1, comma 2, comma 4, correct, because the z value is 4, if we move along the level curve, so let me ask you all this to stop pausing. So if I stay on the level curve where z is equal to 4, is my elevation changing? No. So if I'm moving along this curve and my elevation isn't changing, what's my directional derivative going to be equal to if I'm not changing my elevation? Right, my directional derivative is going to be 0. So if we move in the direction of the level curve, our directional derivative is 0. Okay, hold on to that thought for a second. So if we move along the level curve, our elevation won't change. Which means, well, I want to say this, but it feels like kind of a leap here. So I'll point out, yeah, sure, why not? The gradient, and again, my picture's okay. The gradient vector must point perpendicularly, that's quite the mouthful, perpendicularly to the level curve because of what we just said. Let me show you what we mean by that. So if I said, okay, well, look, I'm going to travel in the direction of the level curve, which is kind of at that moment tangent to the level curve, well, my derivative in the direction of the level curve of my function is still my gradient dotted with my unit vector, which is still the magnitude of the gradient times the magnitude of the unit vector, which s is 1, times cosine of theta. But we just said, you all just told me that if we travel along this level curve, our elevation isn't changing. So our directional derivative has to be 0. And if the directional derivative is 0, and both derivatives are not the 0 vector, right? So typically our vectors are not having a length of 0. So these two parts can't be 0. It has to be the cosine of this angle is 0. But if cosine of the angle is 0, that means the angle had to have been 90 degrees. That's going to tell us that the theta, the angle between the two vectors, is 90 degrees, or pi over 2 if you like. But that exactly means that the gradient vector and the level curve are perpendicular to each other because the angle between them gets you 90 degrees. And 90 degrees gets you 0 change in the elevation. So again, just to say it again, right? I'm asking if we were living at this point right here and decided to travel along the level curve, we would have 0 change in our elevation. But that directional derivative, the way we calculate it is your gradient dotted with your direction of your level curve, which is then equal to this. And then the important part becomes the fact that, okay, the angle between your gradient this way and your level curve that way has to be 90 degrees so that the directional derivative in the direction of the level curve is 0. This was a fact in my brain that took me a long, long time to make it really stick. When I was taking 21C at UC Davis many, many years ago, we learned this fact, and every like week I would be like, "Why is that true again?" I have to like draw a little picture, be like, "Oh yeah, it's because of the dot product." But that's really why this works out. I mean, it's true because it's true, but the dot product helps us see that it is true. That oh yeah, the dot product of these two vectors has to be 0, which means they have to be perpendicular. So that's kind of what's going on here. Let's ask a question using this fact. So let's see here. Yeah. So Another way to think about that is the gradient is the direction of maximal increase, meaning it's got to cross those level curves as quickly as possible. Right? If you're trying to increase your elevation as fast as possible, you're trying to get to the next level curve in the shortest amount of distance. And the shortest amount of distance from like here to there is the line that's going to be perpendicular to both those things. Which again, my picture is probably not doing an excellent job of displaying, but it is true. All right, so here's a question we could ask related to that. So we've got this function, f of x comma y equal to x times y. And the question says to find the gradient of f evaluated at the point 3 comma 2 and use it to find the equation of the line tangent to the level curve f of x comma y equal to 6 at the point 3 comma 2. Okay, and if I read these instructions, I'd be like, "Ugh, what do they want me to do exactly?" Well, they told me to find, let's just calculate the thing they told me to find before I do anything else. So they said to find the gradient evaluated at 3 comma 2. That's not too terrible. So my general gradient here is going to be partial with respect to x, comma partial with respect to y, which is going to be, let's see, the partial with respect to x is y, the partial with respect to y is x. And then we're going to plug in 3 comma 2. So my gradient of f evaluated at 3 comma 2 is going to be the vector 2 comma 3. Okay. All right, so I did the first part, and then I say use it to find the equation of the line tangent to the level curve f of x y equals 6 at the point 3 comma 2. Okay, so the level curve f of x y equals 6, we're really just going to rewrite that as x y equal to 6. And while we could probably graph that, it's much, much easier to graph something if it looks like something you're more used to seeing. If we solve for y here, it's much easier for me to think of graphing y equal to 6 over x. I kind of know what that function looks like. So let's go ahead and graph it. Not that we have to graph it to answer the question, but it helps us see what's going on. So let's see. I know that if x is 1, y is 6. And if x is 2, y is going to be 3. If x is 3, y is going to be 2. And if x is 6, y is going to be 1. It's got your usual hyperbolic shape. I'm only drawing the right half of it, right? There's this whole other left half down here that we don't need to draw for this problem. So we're looking at the point 3 comma 2. So right there. And we're being asked to find the equation of the tangent line. So we want to find the equation of this line right there. We've got the point. That's great. But to find the equation of the line, in addition to having a point, we also need a slope. Well, we can find the slope because we know that the gradient vector is perpendicular to the level curve at the point we're looking. So our gradient vector is going to point that way, right? It's the vector 2 comma 3. So it's over 2 up 3. So there's my gradient vector equal to 2 comma 3. Now I can use that vector to help me find the slope of this green line over here. So let's think about this for a second. What's the slope of our vector? Well, not too terrible, right? Slope is rise over run. So for this one, our rise is 3 and our run is 2. So the slope for our vector is 3 over 2. And then the slope of our perpendicular line, well, perpendicular lines have slopes that multiply to -1. Or another way to say it is they have slopes that are opposite inverses of each other. So the slope of our perpendicular line to that, I should say, the slope of our tangent line that's perpendicular to the gradient here is going to have a slope of negative 2/3. And the rest is just fine. We've got our slope, we've got our point here, which is the point 3 comma 2. And now we can use the slope and the point to find the equation of the tangent line. It's going to be y minus the y coordinate equal to your slope times x minus the x coordinate, which I would probably choose to leave like that. But you could also solve for y if you wanted to. We could write it as y equal to negative 2/3 x. And the negative 2/3 times negative 3 is positive 2. And we add another 2, so it's going to be plus 4. That would also work just fine. Kind of a weird question. Like I feel it feels somewhat contrived, but that's kind of what they're trying to make us use this fact for something. Any questions about anything I've said here? I feel like yeah, it does. Sure. Uh-huh. How do we do this? Nope. Nope, nope. Excellent. How would I do this? That's a good question. How would I do this without the graph? So let's see. So they said find the gradient and use it to find the equation of the line tangent to the level curve right there. So if I didn't have the graph, here's what I would do. I would say, well, my gradient is the vector 2 comma 3. And still at the point 3 comma 2. We're trying to find the equation of the line tangent to our function f of xy equal to xy, which is equal to 6, or if you like, y equals 6 over x. At this point. So here's how we're going to do it. We already have the point on the line, right? The point is 2 comma 3. So we need a point, which is already 3 comma 2. I said 2 comma 3, I accidentally apologize. We need a point, 3 comma 2. And we also need a slope. We're still going to use the fact that the slope of our tangent line has to be perpendicular to the gradient. Or let me rephrase here. I should be saying our tangent line has to be perpendicular to the gradient. So we know that whatever direction, let's say that u, sure, why not? We're going to call u the vector, u points in the direction of the tangent line. I will say it's easier to draw it, but we don't have to draw it. But we don't know what u is, right? So, but we do know that u and the gradient have to be perpendicular. So what we do know for sure is that whatever u is, the gradient of f dotted with u has to be equal to 0. So then what we're going to do here is we say, well, the gradient of f is 2 comma 3. We'll make up something for u, like let's just call it u1 and u2. And if we actually do the dot product here, we're going to get 2 times u1. And you know what would be a better choice than u1 and u2? ux and uy. Just to make it so I can, yeah, that's a better choice here. So then 2 times ux plus 3 times uy has to equal 0. And now just pick something. Whoa. Pick something except for don't pick both 0. Right? If you pick this equal to 0 and that equal to 0, it's not going to help you figure out the direction of your line. So pick ux and uy equal to anything except for 0 and 0. I'm going to pick ux equal to 3 and uy equal to negative 2. That's not the only choice. It's the choice I would make, though. You can pick negative 3 and positive 2. You can pick 3 and negative 2. Those are kind of like the obvious choices here. So then I know that the direction of my line is over 3 and down 2. Right, so my line, u, points over 1, 2, 3 and down 1, 2. That's the direction of my tangent line. Yeah, I had to draw something. So we're going over 3 and down 2. So my slope had better be, well, if I'm going down from left to right, I better have a negative slope. And it's my rise of negative 2 over my run of positive 3. So you could figure it out without drawing the picture there for sure. It just feels like it requires more explaining. And then the rest would still be the same. Good. All right, let's I have a handout for us all to look at. Sorry. Visually. Go, go. So I know there's a few questions on the homework assignment about like trying to estimate the slope of or of the value of the directional derivative. This is kind of getting at that point. So let's take a look at this handout together and we'll see how to do something like this. So what does it say? It says use the contour plot of level curves below to answer the following question. So I'll point out this is definitely the positive x-axis and the positive y-axis. We have here x equals 2, 4, 6, 8, and 10. Here y equals 2, 4, 6, 8, and 10. And here on my level curves, we're saying that along this curve, my function or my surface is an elevation or a value of 4, and then 6, and then 8, and then 10, and 12, and so on. All right, let's look at the question. So they want us to estimate fx evaluated for 4. Okay, what does this actually say? This says estimate the derivative of f in the direction of x at the point 4, 4. So what we're going to do is we're going to look at our graph, our contour plot, and go to the xy coordinate of 4, 4. So we're going to over 4, up 4. So we're right there. And we're asking ourselves, okay, what happens if we move in the positive x direction from left to right? So if we move this direction, well, let's just ask a more broad question. As we move from left to right, is the level curve value increasing or decreasing? Are we moving towards a lower elevation or a higher elevation? Decreasing, right? Moving towards a lower elevation. So for sure, whatever our directional derivative is here, or our derivative in the x direction, should be negative because our function value is getting smaller. So we're certainly going to say that fx at 4, 4 should be some negative number. And now it's really just kind of like making your best guess. So, and this one, I feel like this one is maybe not very well drawn for this, but if we think about it, so let's see. I'd have to go over 1, 2, 3, 4 units in the x direction to get down to the next elevation of 4. So I can say that from here to here, my rise or my change in function value is -2. I'm decreasing by 2. That's my rise. And how long did it take me to get that? Well, I had to go over 4 whole units to get there. So my rise over my run is -2 over 4, or -1/2. Is that perfect? Definitely not. But it's one way to think about it. Sometimes people kind of look at both sides and try like on the other side here, right? If you look at this side here, coming from that direction, it looks like to go from 10 to 8, I decreased by 2, but now over a distance of 2. So another probably valid answer would be something like -1. You're really just trying to get an estimate, a reasonable estimate. So anything between -1/2 or -1, -3/4, right? There's lots of good guesses here. You're really just trying to ask yourself, how much elevation did we drop from as we were moving through this point, as you move from here to here? And it's not easy to tell, right? Because you don't know, like, you only have such limited information. So we're making our best guess. Okay, let's do the same thing in the y direction. So in the y direction, we move this way, up. I can see that from here to here, it takes me about, I'm going to say 1.5-ish units to get to the next elevation value of an increase from 8 to 10. So it looks like my Fy before 4, and I should have said approximately over here, is going to be approximately my rise, which is the change in the level curve value. So if I go from 8, you know what? I just thought of a smarter way to write this. So instead of just writing the difference, I should actually say my rise, well, from 8 to 10, my rise is going to be 10 minus 8. Smart. Here, I could, instead of writing 2 here, I could have written, or sorry, instead of writing negative 2, I could have written 4 minus 6. My ending value divided by my beginning value divided by how much distance we needed to get there. And then here, same deal, from there to there, it looks like the y is changing by about 1.5. So we've got 2 divided by 1.5 or 2 divided by 3 halves, which ends up being 4 thirds. Okay, that seems plausible. It is important here to recognize that we are asking to estimate the slope just at that point, right? So, right, the slope might be changing something like this, and we're looking at this one point right there and asking, okay, right there, what's the slope of the tangent line of that surface? Whereas as you move further this way or that way, it might be steeper or less steep. So again, we're just getting an estimate. Okay, one more question here. Sketch the gradient vector at 4, 4. In what direction as a vector does the gradient vector point? Okay, so I'm starting here at 4, 4. I want you all to try and draw the gradient vector. And remember, the gradient vector should be pointing in the direction of maximal increase. It should be perpendicular to your level curves. So try to draw your gradient vector at that point. To me, it looks like that gradient vector is pointing up and left, right? Not down and right, but up and left, because we have to be pointing towards the larger level curve value, not the smaller level curve value. So we're pointing that way. And if I had to describe this gradient, like if I had, so I can draw it just fine. If I actually had to write it as a vector, it looks like I'm going pretty much equally left and up. So I would describe my vector a couple different ways. You could say that that vector v, well, I'm going, I could write it as just negative 1 comma 1. That'd be totally acceptable. You could also write it as negative I plus j, or whatever other way you choose to write it. In case you haven't seen this, because I had someone else ask me the other day, just as a point of reference here, the vector I is just the unit vector in the x direction. It's the vector 1, 0. And the vector j is the unit vector in the y direction, which is 0, 1. So when you write negative I plus j, you're really writing negative 1, 0 plus 0, 1, which then is just negative 1, 1. Lastly, I'll say that's a fine answer, but what if you said negative 2, 2, and you said negative 3, 3, and I said negative 5, 5? They all point in the same direction. They're all different answers. So if we want to get a answer that is uniform between all of us that's still pointing in the same direction, we would take this vector and divide it by its own magnitude. So a unit vector that also points in that direction is going to be negative 1, 1 divided by the square root of negative 1 squared plus 1 squared. Or in other words, the vector negative 1 over root 2, comma 1 over root 2. Any question? Well, so from this point, I said I have to draw a vector that kind of meets two qualifications. It really needs to, and I didn't really draw this part. It should be perpendicular to the level curve, like that, and should point towards the level curve with the larger value, right? It should be increased, it should be pointing us in the value in the direction where our level curves are increasing, not decreasing. So that was really just I drew it and it kind of looks like it really looks like it's like if I'm thinking about this drawing the origin, it essentially looks like I've drawn the line y equal to negative x, right? But I'm really just making an educated guess. I'm saying it kind of looks like that line. I know that line, the x and y values are kind of the same, except they're opposite. So I know I can say negative 1, 1. Well, it's kind of like the slope broken down into its parts, right? The slope is negative 1, right? So if your slope is negative 1, which is your change in y over your change in x, I'm essentially saying, oh yeah, x can be negative 1 and y can be positive 1 to get that slope. And I do need to say it that way so I go in the correct direction because I'm kind of going backwards here. Just kind of to go along with that point for a second, if if on the other hand, so I can use another company. If I was looking, say maybe, so let's say I asked to find the gradient over here. Well, now if I draw my level curve here, or I should say, sorry, my gradient here, it looks more like that. And there, yeesh, I'm really not in a good spot there. But if I have to guess, well, it kind of looks like I've gone up about 1 unit and I've gone over maybe a half. So I'm thinking, okay, my slope is looking like rise over run, which is a rise of 1 over a run of 1/2, except it's a positive run and a negative rise. So it's looking like a slope of negative 2 or negative 2 over 1. And then I'm going to say, well, so here's the wrong vector to write for this vector I just drew. I could try to say my vector is, well, again, remember that's the y part and that's the x part. So I could say my vector is 1 comma negative 2. But the problem is that's pointing in the opposite direction. Over 1 down 2 is the vector pointing that way. So in this case, I need to flip them both and say, or I should say multiply them both by negative 1 and say that my actual vector is negative 1, positive 2. I'm going left and up, not right and down. But really, it's just to like try to make a decent-ish guess at what the slope might be and then try to find your vector from that. And then lastly, if I wanted to write this as a unit vector, I would then say my unit vector would be this vector negative 1, 2 divided by its own magnitude, which is the square root of 1 plus 4, which is 5. So that would be how to write it as a unit vector. Fair question though, because it is kind of like you just have to look at it and make a guess, which sometimes doesn't feel wonderful. All right, let me do this. Here, we're gonna look at a kind of a lengthy word problem here, but I do feel like your professor likes to talk about the applications to this stuff, and I feel like I should do some of that. I should also keep my papers in order here. Okay, okay. All right, so let's look at this infectious disease model thing, which is kind of a big pain, but it'll be fine. I say more to myself than to all of you. So the infectious disease model. Infectious, I can spell, disease model. And then after that, we'll move on to some other fun stuff. So here's the infectious disease model. You can write this the right way. So R sub 0 of D comma V is equal to 5 times 1 minus V multiplied by D over 1 plus D. Let's talk about what everything represents. So let's get some different colors here. So V is the fraction of the population that is vaccinated. D is the average number of days an individual remains in the population while infectious. And then R naught, this function over here, is the average number of new infections that an infected person causes when put into a completely susceptible population. A lot of words. Susceptible, sure, that's a word I don't know how to spell. Fine. Population. Okay. Before we do anything, I would just like to think about this function for a minute. So this function here is the average number of new infections we're going to get if we put an infected person into a population of people that are susceptible to being infected. So let's ask ourselves, if the population is more vaccinated, we would expect this number to be smaller, right? Because the more vaccinated the population is, we'd expect less people to get the infection. So we'd expect the average number of new infections to be less. And that holds up because if this V number is as big as possible, right, closer and closer to one, right? If 100% of the population was vaccinated, and we're assuming it's completely effective, then you're going to get a 1 minus 1 here, which is 0, and your average number of new infections is going to be 0. It's good to think about like if the numbers really make sense. On the other hand, if D is, we would expect that if D is large, right, you would expect that the more days the person spent inside the population, the more they'd be able to infect more people. So you'd think that if D was larger, you would get a larger value over here. Well, let's see. If D is 1, 1 over 1 plus 1 is 1 half. But then if D is 2, 2 over 1 plus 2 is 2 thirds, which is bigger than 1 half. So as long every day that this goes on, this fraction is going to get larger and larger and larger until you get like, if it was a whole year, which seems kind of ridiculous, but if it was a whole year, right? 365 divided by 366 is a number that's very, very close to 1, right? It's like 0.99, probably off by like 0.03, so like 0.997 or something, but very, very right. So good. This function, increasing or decreasing things, has the results we would expect to happen. Great. Let's look at some things. So, sorry, I gotta read the questions here. So here's the first thing. At a vaccination rate of 10%, when an infected person remains in the population for 2 days, how many people on average do we expect them to infect? Well, that's not too terrible. They're just asking us to put in a few numbers into this equation. So we'd expect that the average number of new infections for a person that's in the population for 2 days with a vaccination rate of 10% or 0.1 is going to be 5 times 1 minus 0.1 times 2 over 1 plus 2, which ends up being, let's see, 5 times 0.9 times 2 thirds is going to be something. I think it's 3. Let's see. 5 times 2 is 10. 0.9 divided by 3 is 0.3. So you have 10 times 0.3, which is 3. So if only 10% of the population is getting vaccinated, and we take some infectious person and put them in the population of susceptible people for a length of 2 days, we'd expect them to infect 3 other people. Okay. Let's ask more interesting questions. And that question was really just about making sure we understand how the function works. Yeah. Good question. When? Never hesitate to ask me what something is written because I know that my handwriting, especially when I get going, can get a little bit sloppy. So let's look at the next question, which is going to be the following. Suppose any reallocation. So reallocation meaning we're taking whatever resources we have to either make it so more of the population gets vaccinated, or we're able to keep people out of the population or not in the population, infects people out of the population sooner, right? Those are the things we can affect. So we're going to reallocate resources so that we can achieve maybe better results. And here's kind of our framework. Suppose any reallocation of resources results in D increasing, which we don't want, twice as much as V. Twice as much as V. Right, we want to increase V. We'd like to decrease D if possible, but that's not what we're given here. So what we're going to do is we're going to use a directional derivative to determine if this is beneficial. Okay, well, first of all, what does it mean to be beneficial in terms of our function, R? Do we want R to get bigger or smaller? Smaller, right? So beneficial meaning, is it going to decrease or not? Well, let's check it out. So here's our function again. R naught of D comma V equal to 5 times 1 minus V times D over 1 plus D. So good news, they told us what to do, so we don't have to think that hard, at least at first. So they just asked us to find the directional derivative. So let's go ahead and find our gradient, right? So we need the gradient to find the directional derivative. So I should point out a couple things. So we want to find the directional derivative, aka the rate of change of our function, R naught, in what direction? Well, they told us, but they didn't tell us how they told us exactly. So they're telling us how our reallocation of resources works. We know that if we increase D by, or I should say, if we increase V by 1, D is going to increase by 2 because D is increasing twice as much as V is. So, question, is the vector 2, 1 or 1, 2? How do we know? It totally is dependent on the way we've decided to order the variables. So in this problem, since our function is a function of D first and V second, the D thing has to be the first part of the vector and the V thing has to be the second part. But it's really like if you wrote it as V comma D and just did that, then it would be 1, 2. So here, our direction vector is the direction of, let's call it V. No, let's not call it V. We're already using, let's call it W equal to 2 comma 1, right? D increases twice as much as V. All right, so we've got our direction vector almost. We are going to have to normalize it because, right, it always has to be a unit vector. But before we do that, let's go ahead and find the gradient. So our gradient here, our del R naught, is going to be the partial derivative of R naught with respect to D, comma, the partial derivative of R naught with respect to V. Which is not the funnest thing to find. So let's not write this all in the vector notation here, because actually finding the partial derivatives is a little bit ugly. So let's find our del R naught del D first of all. All right, the 5 times 1 minus V is just going to hang out. That's a constant multiple. The D over 1 plus D, we're going to have to take the derivative of using the quotient rule. So it's going to be the bottom 1 plus D times the derivative of the top, which is 1, minus the top, which is D, times the derivative of the bottom, which is also 1, all divided by the denominator squared. And you might as well simplify this because we can. That's going to be 5 times 1 minus V. The 1 plus D minus D ends up just being 1. So that's going to be times 1 over 1 plus D squared. And I should apologize. I left out one piece of, or I kind of left out one piece of information, not on purpose. We're assuming that we're starting at the place we were in the previous problem. So our starting value is, we're starting with V equal to 0.1 and D equal to, I think it was 2. Yes, it was. So that's the point that we're going to find the direct. So we're starting at this point on the surface and asking, cool, what direction can we travel on the surface to make the function decrease as rapidly as possible, not increase. So we'll get to that. All right, so there's my directional derivative. Sorry, there's my partial derivative with respect to d. Let's go ahead and plug in my point so we can find the value. So if we plug in the value of, make sure you write it in the right order, 2 for d, 0.1 for v. Well, we already found what that was, right? Oh, no, no, I'm a liar. We found what that was when you plugged it into the original function, not to this function over here. Let's plug it in. So you can get 5 times 1 minus 0.1 is 0.9, and 1 over 1 plus 2 squared, that's going to be 1 over 9. That works out pretty nicely. That's 5 times 0.1, which is 0.5. Cool. That was not as ugly as I expected it to be. And then we'll do the same thing for the other partial derivative. So there's one of the partial derivatives. The other partial derivative is going to be del R naught del V. That one's actually much easier to take because you're just going to get 5 times the derivative of 1 minus V is -1, and then you still have your D over 1 plus D. And then plugging in our values, our del R naught del V evaluated at 2 for V and 0.1 for D is going to be -5 times 0. Whoop, not 0.1. I'm plugging in 2 for D. 2 divided by 1 plus 2. So let's say we're getting -10/3. All right, so finally, our gradient is equal to, I'm going to write them both as fractions, del R naught del D, which is 1/2 or 0.5, and del R naught del V, which is -10/3. So then we're going to dot these two vectors together, our gradient vector and our normalized direction vector. So our del R naught dotted with, instead of W, we're going to write W divided by the magnitude of W. That's just going to equal our 1/2 comma -10/3 dotted with 2 comma 1 divided by, what's the magnitude of that vector? Yeah, square root of 5. So then we get something. Let's see, we get 1/2 times 2, which is 1, plus -10/3 times 1, which is -10/3, all over root 5, which I guess we could simplify as 3/3 minus, so -7/3 over root 5, or -7 over 3 root 5. And I think I said something before that was kind of not true. I said something about like this I yeah I said something about pointing in the wrong direction. That is not the case. So I should point out this gradient vector, that vector points in the direction of maximal increase, which is kind of like the opposite way you want to go, right? But I'll point out that the thing we've done, right? So reallocating results in this direction of 2 comma 1 is going to decrease R naught, right? Because our derivative is negative. And that's good in this case, right? We wanted our R naught to be less because we want I forget what R naught was exactly, right? R naught's the average number of new infections that an infected person causes. So if R naught is smaller, we've done a good thing. We've reallocated resources in a way that's beneficial to stopping the spread of this particular disease. I feel like there's a much more of a reading problem than it is a math problem, which in this class is not sometimes the case, I'll say, right? There are sometimes the problems that really require a lot more reading and interpreting, or as much reading and interpreting as there is math. So we'll ask one more question, and then we'll move on. And I'll explain kind of a couple things in this question. So in terms of ratio of changes in D and in V, what is the best possible strategy for I'm going to insert a word right here in a second, so leave a space for a 5-letter word here, for a reallocation of resources. Now, the thing I have to include here is the word small. And the reason why is because if you make a large allocation of resources, that's going to push you in a direction where eventually your directional derivative is going to be something different later on. So we're talking about just at this one point on this surface. The real question is asking, what directional derivative can we take, or what direction should we take the directional derivative in to, at this point, to decrease the function's value as rapidly as possible? That's why we have to say a small reallocation, because we're only looking at this one point. And once we've changed things enough, then we're at a different point, and then you have to have a different answer to that question. That's why we're using the word small there. So here's what we want. So again, we're looking for the best possible strategy, meaning we're trying to decrease R naught as rapidly as possible. So this is kind of a really nice point here, but we're about to see. But I like to think about, there's a question sometimes people ask is like, you're out skiing on a slope and you want to go downhill as quickly as possible. Well, you know what direction is downhill as quickly as possible? The direction that's opposite uphill as quickly as possible. So if you're trying to decrease as rapidly as possible instead of increase as rapidly as possible, your direction should be the opposite direction of the gradient vector, or in other words, the negative of the gradient vector. So to decrease as rapidly as possible, the direction needs to be the negative of your gradient vector. Good news, we already know what that vector was. We did it in the previous part of the problem. Our gradient vector last time was, let's see, it was 1/2 comma negative 10/3. So in this case, we could say the answer to this question is going to be that the negative of that gradient vector is just negative 1/2 comma positive 10/3. And I will admit, this is not a unit vector. I still kind of want to just leave it as it is. But if you want to make a unit vector, you can say, or the unit vector negative 1/2 comma 10/3 divided by the square root of negative 1/2 squared plus 10/3 squared, which seems like a pain in the butt. But that would also be fine. I would definitely say it's worth asking your instructor if he wants you to always normalize your direction vectors. It's typically true in web work because that's just kind of how it's designed. But on your exams, you might want to ask for clarification there. All right. So that's pretty much all there is to say about the gradient and directional derivatives. They're again, let me just sum up here by reminding you one more time. So the directional derivative, once again, is just the gradient of f dotted with the unit vector in your direction you're taking the derivative in. And then the direction of maximum increase or maximum slope or steepest slope, however you want to say it, is always going to be the direction of the gradient vector. And if we write it as a unit vector, it's its own gradient vector divided by its own magnitude. And then thirdly, the value, the maximum value of the directional derivative is always the magnitude of the gradient. And the last thing is that the gradient is always going to be perpendicular to level curves. So just to sum up the things we said one more time. Those are the things we said. Cool. So with our last 13-ish minutes here, let's start talking about how we're going to find maximum and minimum values of functions of two variables, which I think is kind of an interesting topic. And instead of trying to draw this picture, which I'm not good at drawing, let me just show you a picture real quick. So let me give you a second to write down whatever you want to write down. I'm going to show you a picture. All right, here comes the picture. So here's the picture we're looking at. Let me see. Can I zoom in? Yes, I can. Cool. Can I move this around a little bit? Nope, I can't. Okay, fine. There we go. So we're trying to find, oh, that looks really yellow. Interesting. So we're trying to find maximum, minimum values of a surface. So it's either going to be a highest point or a lowest point, or there's also this weird saddle thing going on. And the idea is that at any of these points, if you're at the highest point on the surface, then in any direction you travel, the slope should be a slope of zero. Because you're right at the top, right? Whether you move forwards or backwards or left or right or diagonally this or diagonally, your slope is zero for at least that moment, right? And then as soon as you move down, like then your slope is along zero. But right at the top, at that instant, your slope is zero. Or at the bottom, right? If you're at the bottom of the surface, even though you kind of be like weirdly upside down, or like I guess you'd be in like the bottom of a hole, maybe, right? Like if you're like on right, if you're on top of that surface there, you can't see where I'm pointing. That doesn't help you at all. I'm like pointing, like look right there. Can't you see? No, sorry. If you look right there is where I was pointing to. You can imagine being kind of in a container at the bottom, and at the very, very bottom, right, the slope of the surface is flat for just a second, zero. And then we also have this other one over here. Stop pointing at things like that right here. So that tangent plane, in fact, all three of these tangent planes have a slope of zero. They're parallel to the xy plane. And although you could say the derivative in every direction is zero, you only have to say the derivative in two directions is zero, specifically the x direction and the y direction. Because if you have a tangent plane where both those directions have a derivative of zero, the whole thing is flat, or you have no other choice. Because your tangent plane would just be a constant if you're partial, right? Remember how to find the equation of a tangent plane? It's the derivative in the x direction times some stuff, plus the derivative in the y direction times some stuff, plus a constant. Well, both those derivatives are zero, then your function is just equal to a constant, which means it's flat. It's parallel to the ground. The interesting thing about the last tangent plane there for that saddle is that tangent plane lives both above and below the surface, right? It's below the surface in the y direction. It's above the surface in the x direction. It's kind of like how at an inflection point on a curve, the tangent line is both above and below the curve. Kind of a similar idea. Right? Is everyone cool with what I'm talking about? Just in case you're not cool, just so I can make my point really clear here, what I'm saying there is that if you have a curve with some inflection point, which is probably about right there, well, everywhere where the function's concave down, the tangent lines live above the curve completely. And everywhere the function's concave up, the tangent lines live below the curve. But at the point where we transition from concave down to concave up, well, the left half of that tangent line is above the curve and the right half is below the curve. So there's one tangent line that actually goes through the curve. And in a similar way, that picture, which I know is gone now, forever maybe, right, that tangent plane is sitting both above and below the surface because saddles are weird. Okay, so anyway, that's what I want. That's the picture I want to show you because I'm not, I mean, I could draw it, but I shouldn't. Okay, so let's look at some stuff. So the whole idea here is really kind of stuff you're already used to doing. We're going to find maxima, minima, very similarly to how we did in 17a by finding critical points of the function by which we find by setting derivatives equal to zero. And then we're going to classify those as a max or a min based on a similar test you used back in 17A. In fact, before we do this, let's actually remind ourselves of that test because I do want to, it is going to be important. So let's look at one example from 17A. Let's say we want to find the maximum and minimum of f of x equal to x cubed minus 6x squared on the interval. Nope, not on any interval, just in general. Find the, I should say, the relative maxima and minima because this function doesn't have any absolute. And we're not talking about absolute yet. We're talking about relative. So, usual process. Take your first derivative, which in this case is going to be 3x squared minus 12x. Sure, that's fine. Yeah, that's fine. Set that equal to 0. I'm going to factor out a 3x, left with an x minus 4. So I'm going to get either x equal to 0 or x equal to 4. Now, I will point out where we're going, it's important to have both the x and y coordinate for your critical point. Here, it's not so much, but you could say, right, the critical point is actually technically 0, 0 and 4, 64 minus negative 32, I think. But then, not so important here. The real thing I want to ask is, for each of these, are these relative maxima or relative minima? Or neither. Could be neither. Okay, here's how we're going to check. Not because you do it this way necessarily for this, but we're definitely going to do it this way in the future. So instead of doing the first derivative test, we're like the function increasing, decreasing, or decreasing, increasing. We're going to use the second derivative test. So the second derivative test here says you take your second derivative. So my second derivative is f double prime of x is going to be 6x minus 12. And then you plug in each of your critical points. So if I look at f double prime of 0, I get 6 times 0 minus 12, which is negative 12, which importantly is negative. What does that tell us? So let me ask you another question. What does the second derivative being negative tell us about the concavity of the function? Is it concave up or is it concave down? Concave down, right? Because it's negative. Cool. So if it's concave down, but you know the derivative is equal to 0, it's got to be at that point right there, which means we have a relative maximum. So if your second derivative is negative, you get a relative maximum. So x equal to 0 gives a relative, gives whatever, is a relative maximum, is a relative maximum. Similarly, if we plug in positive 4, we're going to get 6 times 4 minus 12, which is positive 12, which is positive, which means our function is concave up. And at that critical point, which is again a place where the derivative has to be 0, because we found it that way, that means it's going to be a relative minimum. So x equal to 4 gives us a relative minimum. And that idea is how we're going to classify our relative maxima and minima for functions of two variables. But there's just a little more work involved. So, sure. So let's look at this. How much time have I got? Oh, I got time. So let's look at this first example. Yeah. So here's a relatively easy example. Find and classify all local extrema of the function f of x comma y equal to x squared plus y squared minus 2x plus 4y plus 3. Right. So we're going to find the critical points by not just setting the derivative equal to 0, but setting each of the regular partial derivatives equal to 0. Because again, remember that picture, we need both fx and fy to be 0 so that our tangent plane is flat, parallel to the ground. So our fx is 2x minus 2. We're going to set that equal to 0. And we're going to get x equal to 1. X equal to 1 is not a critical point on its own. You have to have a y coordinate as well. So then fy is going to be 2y plus 4. Set that equal to 0. You're going to get y equal to negative 2. So our only critical point is the single point 1 comma negative 2. We don't need to include the z coordinate, although you could if you wanted to, right? If you plugged in 1, negative 2 for x and y, you would get whatever this function was equal to, which would be the z coordinate. But I don't really care. All I know is that my surface, whatever it is, has a plane tangent to it at that point that is flat, that has a slope of 0 in any direction. Okay, so now we're going to we're going to classify this critical point. So how to classify? Well, it's not exactly the second derivative test. We have to calculate this other thing, which I might as well tell you. You don't need to know this next part, but this thing we're going to calculate is the determinant of a special matrix. It's called the Hessian matrix. Not important, but it is coming from the fact that we're going to take the determinant of the 2 by 2 matrix of second partial derivatives. So it's fxx, fxy, fyx, fyy. And the determinant is fxx times fyy minus fxy times fyx. And fortunately, fxy and fyx, the mixed partials have to be the same because of the kind of functions we're dealing with. So really, our thing we're going to use to classify, this determinant is going to equal fxx times fyy minus fxy quantity squared. You definitely will want to memorize that. It's going to come up often. So first we're going to calculate this. Now this problem is going to be not that interesting because, well, you'll see. So here we're going to calculate d. It's going to be, let's see, fxx is going to be, the second derivative with respect to x is going to be 2. Fyy is also going to be 2. And fxy or fyx is going to be 0. So d is equal to 4. So we'll touch more on this next class, but I'll tell you right now, if d is negative, you get a saddle. Because if d is negative, what's essentially happening is in one direction it's concave up, and in one direction it's concave down. But we're not there right now. Our d is not negative, our d is positive. So if d is positive, what that means is you either have a maximum or a minimum. People get this twisted a little bit though, so I want to really, really emphasize here. If d is positive, there's more work to do. You have to figure out is it a max or min, but it's really, really easy based on what we just said. We know here, hey, look, our second derivative, fxx, was equal to positive 2. So that means that my surface is concave which way? If our second derivative is positive 2. It's got to be concave up. It's also, so it's concave up in the x direction. Also, since fyy is positive 2, it's also concave up in the y direction. What we really have here is an upward opening paraboloid. And so we definitely have a minimum because either one of my second partial derivatives was positive, and we were concave up, and we had a minimum. So 1 second. So here's what's going to happen every time. You're going to calculate this. If it comes out negative, it's going to be a saddle. If it comes out positive, either both of these things were positive and multiplied to give us something positive, and so they're both concave up, or both of these things were negative and they're both concave down, giving us a maximum. But these two things have to be the same sign, well, kind of ish, enough to get either a max or a min. If these two things are different signs enough, and again, we'll touch on this more next time, you're going to have a saddle. So the thing to take away here is that if d is positive, it's either a max or a min. It's a maximum if your second derivative is negative. It's a minimum if your second derivative is positive, again, because of the concavity. On the other hand, if d is less than 0, it's a saddle point every time. And here's the bad news. Just like the second derivative test in 17a, if it's equal to 0, you don't know. So if d is equal to 0, we don't know what we've got. All right, that's all I got for today. See you all on Thursday. If you didn't get your name on the sign-in sheet, please make sure you get your name on the sign-in sheet.